There are 4 laws of thermodynamics, 4 tenets by which we can describe why all chemical reactions happen. Each of the 4 laws give birth to an important thermodynamic concept. The first of these laws is actually given the name the Zeroth Law, as it was perhaps a bit of a thermodynamic afterthought. To think about this thermodynamic law, we are first going to consider a mechanical axiom. If we have 2 systems, each containing a gas connected by a frictionless piston, and my piston moves, in this case from left to right, I can say that when the piston was moving, the pressure in the left-hand system, system A, was higher than that on the right, system B, and when the piston came to a stop, the pressure was the same in both of my containers. Now, if I introduce a third system, system C, if that system is in mechanical equilibrium with system A, then the pressure in both A and C is the same. We have already established that A and B are in mechanical equilibrium with each other. Then it is just common sense to say that the system B and C must also be in mechanical equilibrium. Or the pressure in all 3 containers is identical. Extending this to my thermodynamic system, here I can say that if 2 systems are connected with a diathermic wall, then they can transfer energy in the form of heat. If no energy is being transferred, then system A is in thermodynamic equilibrium with system B. If I introduce a third system, C, and that is in thermodynamic equilibrium with A, then it must also be in thermodynamic equilibrium with B. In fact, this is just a statement of the Zeroth Law of Thermodynamics. If A is in thermal equilibrium with B, and B is in thermal equilibrium with C, then C will be in thermal equilibrium with A. There are many other equivalent statements of this law, but this version is perhaps the most common. However, what does this actually mean? What do we mean by thermodynamic equilibrium? Well, I've already mentioned that each of our laws in thermodynamics gives rise to a concept. Previously, I stated that if 2 systems were in mechanical equilibrium, then the pressure was the same in both. I asserted this concept of pressure on my example by knowing that the systems were in mechanical equilibrium. For the idea of thermodynamic equilibrium, the property I am describing as being equal in both systems is temperature. I will cover in other videos what temperature is in terms of the properties of our system, but here conflating the terms thermodynamic equilibrium and of equal temperature is reasonable, and this is in fact the basis of a thermometer. A thermometer, if left in a sample, is allowed to come into thermodynamic equilibrium. Given a property changes with differing temperature, such as molar volume or resistivity, we can then give a value for this temperature, for this thermodynamic equilibrium. Thermodynamic temperatures are based on the Kelvin temperature scale, and the unit Kelvin is one of our 7 base SI units. There is more information on temperature in other parts of this course, but for now, thank you for listening, and don't hesitate to contact me if you have any questions.